Hi, I'm Imeni Yahyawi and I will present the essential of our work titled Development of Thermochemical and Electrical Model for a Solid Oxide Fuel Cell. This work is prepared by Stefani Vanussi Melo Guatoloni, Giussara Farias Fardi, Lucas Frisera Encarnacion, Fernando Tadeo, Katia Taila Silva de Melo, and me. The presentation will start by an introduction about solid oxide fuel cell, then followed by presenting the paper goal. Then I continue the presentation with the proposed thermochemical and electrical model, followed by heat exchanger model, reformer model, anode model, cathode model, and combustor model. Then I will explain the electrical model and the validation and performance analysis of the proposed models. The presentation ends with conclusions. The solid oxide fuel cell is a type of fuel cell that works at high temperature values, usually between 650 grade Celsius and 1000 grade Celsius. This high temperature make possible to provide electric power from a variety of fuels, not only natural gas, but also biogas from different sources. As the exhaust gases have high temperatures, they are frequently used in combined heat and power cycles, increasing the overall system efficiency. In addition, the high temperature makes possible to use a non-noble catalyst, which reduces the cell cost. A disadvantage of the high operating temperature is the sensitivity of the water vapor content. It means if there is no sufficient water vapor for the reform process, the methane molecule decomposes into hydrogen and solid carbon, which might clog the process of the anodes, leading then to cell degradation. In this sense, this paper proposed a static model of the tubular SOFC with anodic recirculation, which is implemented in PSCAD software in order to provide a platform for such fuel cell implementation and operation. The proposed model contemplates the thermochemical and electrical analysis in an interconnected way, allowing to find the operation point of the fuel cell corresponding to the highest power or the highest operation efficiency. The proposed model consists of 7 subsystems. A subsystem for the 2 heat exchangers, heat exchanger 1, heat exchanger 2, 1 reformer, 1 anode, 1 cathode, and combustor model. Then we have the electrical power model that allows to calculate the electrical power generation. The heat exchanger models too has the function to heat the fuel entered gradually. This prevents it from self-combustion if the fuel encounters a very high temperature gradient upon entering the reformer. The heat exchanger 1 has the function of heating the atmospheric air that is inserted in the cell through the heat exchange with the combustion exhaust gases. To obtain the molar flow of each component of the gas mixtures in kilomole per second, the following equation is used. To perform the mass balance calculation, this balance should be ensured. To carry out the energy balance, first equation to follow is used for the cold gas, the fuels, and second equation for the hot gas. This corresponds for the cold gas, and this equation corresponds for the hot gas. The calculation of Cp needed for the energy balance is done according to the equation below. In the reformer, the water molecules coming from the anode outlet react with the inlet gas in a reform process. The calculation of the mass balance is as shown before. To calculate the energy balance, the following equation is used. At the anode, the hydrogen ion reacts with the oxygen ion to form water. In addition, what's left of methane is reformed. The calculation of the mass balance and energy is equivalent as shown before. For the cathode model, the breaking of the oxygen molecule from the atmospheric air and the association of the resulting ion with the electron separated thanks to the hydrogen in the anode is moderate. The oxygen flow sent to the anode is calculated by the following expression. The calculation of the mass balance and energy balance is equivalent as shown before. For the combustor model, all the gas leaving the anode and the cathode are in the combustor. The only gases capable of reacting under the conditions of temperature and pressure there are in the combustor are dihydrogen and oxide carbon. They react with oxygen and a complete combustion between hydrogen and carbon monoxide with oxygen is considered to occur. The calculation of the mass balance and energy balance is equivalent as shown before. The model of the electrical generation is explained now. With the information that originates in the cathode and the anode of the cell, it's possible to calculate the electrical parameters, and they are obtained from the thermodynamic information of the cell's operation. And this makes possible the electric study of the cell with variation of non-electrical parameters. To calculate the reversible voltage generated by the cell, the following expression is used. During the cell operation, two of the three main energy losses decrease the voltage generation. These losses are modeled as following. They are classified into activation losses that for which the yield is described by the following expression, and we have the ohmic loss that are described or modeled by these expressions. The current supplied or generated by the cell is given by the following expression. So using this expression and the equation of the voltage, it's easy to deduce the power generated by the cell. The efficiency value of the cell can be obtained by the following ratio. For the model validation, a comparison between the proposed model and three models in the literature is performed. To do so, a comparison in terms of power, voltage, recirculation, temperature of the SOFC cell, the temperature before cathode, the combustor temperature, the exhaust temperature has been compared with the model proposed in the reference 12. It's clear here that the error between the proposed model and the models proposed in the reference 12 is acceptable results. Then here in table 2 we present the validation of the model of the proposed model for the SOFC, comparing it with the results presented by the reference 30. Also here we can notice that the error between our results and the results presented by the reference 13 is a good result. Finally, We also compared our model with the model proposed in the reference 14. It's possible then to demonstrate that the modeling developed represents well the full cell operations in the errors. Comparing the results of our models and the three models represented by the reference 12, 13, and 14 are good results. The error in the values calculated from this model was not greater than 4%. The performance of the developed model has been tested by the implementation of a tubular SOFC in the city of Victoria, Brazil. The cell must work at the best point of operation considering local conditions. The characteristic parameters of the atmospheric air and natural gas used in this study are shown in Table 4. The cell chosen to perform the simulation for a possible implementation was the tubular SOFC with internal reforming and combustor produced by Siemens, Westinghouse, EDB, Elsam, CHP 100, whose characteristics parameters are found in Table 5. The parameters consist of a power of 110 kilowatts, a current of 295 ampere, an efficiency of 46%, etc. The effect of the pressure increase is presented here in these figures, where the power and the oxygen partial pressure are presented in function of the pressure. In fact, these results show that when the oxygen partial pressure increases, when increasing the pressure, this allows the power generated by the fuel cell to be increased too. Also, the efficiency of the fuel cell is increased. The variation in the air-fuel ratio changes the atmospheric airflow in the cell. Also is demonstrated here in these slides. Indeed, the electrical power generated here decrease when the air-fuel ratio increase. Thus, this leads that the temperature of the cell temperature decrease also due to the increase in the air-fuel ratio. The effect of the amount of flow recirculated to the reformer also is demonstrated here. In fact, the higher the percentage of the recirculated flow, the greater the energy generated and the efficiency. This happens due to the decrease of the electric current generated. In the analysis of the variation of anodic recirculation percentage, it's clear from the result that from 85% of anodic recirculation, the power and efficiency begins to fall. This is because with the increased recirculation, the hydrogen partial pressure drops. However, from a certain value, the amount of hydrogen becomes so small in the anode that the concentration polarization increases and the cell voltage decreases. As conclusions, this paper has presented a model that describes the behavior of an SOFC cell in operation conditions from the information of fuel composition and atmospheric air. It has also been shown how this model makes possible to find a point of higher efficiency for the cell and thus the point of greater power generation. To validate the model, 3 simulations have been presented using the information in the work found in the literature. The results reproduce the performance reported in those previous publications. This shows that the model is valid and can be used to provide the behavior of tubular SOFCs in normal operation regime. A study on the implementation of the city of Victoria of a 110 kilowatt SOFC by Siemens, Westinghouse, Brazil was presented. The local information on the composition, temperature, pressure, and flows of the atmospheric air and the natural gas supplied at the site were used to obtain operating parameters that would provide greater power from the cell. Through the atmospheric air pressurization, an increase of 11% in the power generated by the cell was achieved without a fuel increase. With anodic recirculation of 85% of anode leaving gases going to reformer, an increase of 8.7% of power generated by the cell was achieved without increasing fuel consumption. The study could be applied to related case studies by using the developed models. Here are the references used in this representation.